Hello, Matthews, Gatos here. Welcome to Chapter 11, Permutations, Combinations, and the Binomial Theorem. In this video, I'm going to do Part 1 of Lesson for 11.1 Permutations. So in this lesson, we're going to be looking at solving problems using the fundamental counting principle, the number of permutations, and how to solve counting problems when we have identical elements and restrictions, and of course, solving equations using the formula. Let's get off and start about what a permutation is. A permutation is just an arrangement of objects. So let's say for a minute you have 4 coins, or a coin that you're going to toss four times. I want to know how many possible outcomes there are when I toss that coin. So the very first time I toss the coin, I can get heads or tails. But then it starts to branch out from there. So if I get heads on the first coin, I could then on the second coin again get heads or tails. Same thing if I got tails here, it could branch out and get heads and tails again. So I end up with that. So right now, tossing a coin 2 times, I have 4 outcomes. Heads, 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 tails, tails, heads, tails, tails. If we add on another coin, each one of these outcomes also branches out 2 times. So now we're at 2 outcomes for 1 coin, 4 outcomes for 2 coins, and we're at 8 outcomes for 3 coins, and they branch out 1 more time, and here are all the possible outcomes. There are 16 outcomes altogether. Now that wasn't so bad because it was just a little simple tree diagram, but sometimes I could ask you something like how many times or how many outcomes are there if I toss a coin 100 times? And I don't want to list out all the outcomes for 100 times. So this brings in another way of doing a question. When I don't want to list out the outcomes, I just want to know how many outcomes there are. So I want to be able to count how many outcomes there are. I can do that using what's called the fundamental counting principle. So the fundamental counting principle says if one task can be performed m ways and a second one n ways, then altogether there are m times n ways of that task being able to be performed. So let's go back to that coin example. We already saw listing them all out. There were 16 outcomes. If I wanted to use the fundamental counting principle, each coin had 2 choices, heads or tails. So coin 1 had 2 choices, coin 2 had 2 choices, and so on. And fundamental counting principle tells us to multiply these numbers together. So you can see 2 times 2 times 2 times 2, 16 outcomes altogether. So we're going to use this fundamental counting principle to find the number of outcomes, not list all the outcomes out, just determine how many outcomes there are. So in this example here, we have library books having barcodes. Now the barcode has 14 digits. The first 8 digits are always going to be 318470. So this will always be what the first numbers are. The remaining 6 numbers can be filled by any digit. So I want to know how many barcodes are available. Now, if I can fill it by any digit, just to make sure we're all on the same page, there are 10 single-digit numbers, 0 through 9. So I'm going to use the fundamental counting principle to determine the number of choices. Now, when I use these little dashes, the key to me for using fundamental counting principle is labeling each little dash, so you know exactly what each stage of the fundamental counting principle represents. So in the very first stage, I can only have one choice. It has to be 318470. And then it said it can have any digits, 6 digits after. It didn't say anything about repetition not being allowed, so I can safely assume there are 10 choices for this digit, 10 choices for this digit, and so on. So if I were to multiply all of those together, that would give me the total number of barcodes possible. And so I do exactly that, and I can see, looking at my answer here, that there are 1 million possible barcodes at this library. Okay, this is a diploma example. So the diagram below shows a seating chart for an aircraft. The seats shaded black have already been reserved. The lighter shaded seats are available. So there are 12 seats available, 7 customers. I want to know the number of different ways they could be assigned a seat. Okay, so I don't want to list out all the different combinations of seat selection. I just want to look at how many choices are possible. So I'm going to do this in terms of the customers. I have 7 customers that I am putting in seats. So first customer comes up, looks at the diagram. That customer has 12 choices of a seat. Now they choose their seat, and the next customer doesn't have 12 seats anymore because the first customer just chose a seat. They have 11 choices. And you can see I've written a note there. The number of choices are going to go down by 1 as each customer picks their seat. So customer 3 has a choice of 10 seats because the other 2 customers chose their seat, and then 9, 8, 7, and 6. So to find out the number of ways that I could assign the seats, I just multiply those together, and I get that there are 3,991,680 different seat selections for 7 customers choosing 12 seats. Okay, this one here we have a flyer. So a manager wants to show the 5 tents shown below on next week's flyer. So we have a dome, a hiking, a rain, a roomie, and a riser tent. In the flyer, the dome, rain, hiking tents are yellow and the riser tent is blue. The roomie tent is red. The yellow tents can appear in any order but cannot immediately follow another yellow tent. So they just want to kind of spread out the colors. So if I look at that, I can see that there are 3 yellow tents, and if I don't want them to be side by side, I have to fit the red or the blue in between each of the yellow. In other words, the yellow is going to be alternating. So I know it's going to look like this. I have my yellow, a yellow, and a yellow, and in between the red and the blue go. So for my first yellow tent, there are 3 tents, so I can choose from any 3 of them. Let's just focus on the yellow first. So I choose that yellow tent. For the second yellow tent, I have 2 choices. And for the third yellow tent, I only have 1 choice. So now that I've done the yellows, let's go back and look what goes in between. So in between yellow 1 and yellow 2, it could be a red or a blue tent. There are 2 choices. Once I pick that, the tent in between yellow 2 and yellow 3 is whatever I didn't pick. So in other words, if I picked a red here, it would have to be a blue. If I picked a blue here, then this one would have to be a red. So this here, there's really only 1 choice. So I just multiply those together and I see that there are 12 different ways I could do that on a flyer. So again, to me, the key in the fundamental counting principle is this part right here. The better I label it, the easier it is for me to identify my choices. And then just remember you're multiplying all your numbers together. Okay, so we have a bank machine PIN consisting of 4 digits. We want to know how many codes are possible. So my first question to you is, can a 4-digit PIN start with a 0? So could you have a code, for example, 0123? And the answer to that, yes. Okay, so yes, you can have a 4-digit PIN because a PIN is not a number. Okay, my second question to you is, can a PIN have repeats? So could you have a code that was, say, 1123 or 1112? And the answer, yes, you can have as many as you want. Okay, so yes, as many repeats as you want. So as many repeats as digits is possible. Now, you'll notice that this question didn't say anything about repeats, and this is an important note. Repetition is always going to be allowed unless otherwise stated. So if they didn't want repeats, they would say, a bank machine consists of 4 digits. How many codes are possible if no digit repeats? So because it doesn't say that, I can safely assume repeats are allowed. Okay, so I have a 4-digit PIN. It can start with 0, can be repeated. Remember, there were 10 digits. So really, I have 10 choices for every single one of the digits. So multiplying those together, I can see that there are 10,000 4-digit PINs. Let's start to put some restrictions on things just to see how that would play out. What if I say, how many 4-digit bank codes or PINs are there that start with a 9 and don't have any repeats? Okay, so repeats are not allowed. So it has to start with a 9, and then the second digit can't be the first digit because repeats aren't allowed. The third digit can't be the first or the second, and the fourth digit can't be the first, second, or third because repeats aren't allowed. So looking at this, my first digit has to be a 9. So there is only one choice there. Okay, now I have 10 choices and it can't be whatever my first digit was. So 10 digits to choose from, it can't be whatever the first is. So really I have 9 choices for that digit. So I have 10 digits. This third digit can't be the first or the second, so there's 2 restrictions. 10 take away 2 is 8. And this last one can't be the first, second, or third. So 10 choices, I have to take out the 3 I've already chosen, which is 7. And you'll notice I wrote here the number of choices minus the number of restrictions. That will be the choice for each stage of the fundamental counting principle. Okay? So I can multiply those together and I get that there are 404 4-digit pins starting with a 9 and having no repeats. Okay, in this question here, I want to know how many 4-digit bank codes have at least 3 threes. Okay, so keyword there is at least. Now, at least means a minimum of 3 threes. So since I have a 4-digit bank code, I either am going to have 3 threes or 4 threes. Because there are 2 separate choices, these are like cases, 2 separate cases. So I have to look at each case. So the first case being I have 3 threes. The second case being I have all 4 threes. Well, the second case is pretty basic. Your pin is going to be 3, 3, 3, and wait for it, 3. So there's only really one way of doing that. The 3 threes is where it's a little bit more difficult because it didn't say that it was 3, 3, 3, and then another number. It could be 3, another number, 3, 3. So those threes could be in any kind of a position. So my fundamental counting principle looks a little bit different now. So you can see I can have, in my first case, 3, 3, 3, not 3. So 3, 1 choice, excuse me, 3, 1 choice, 3, 1 choice. And then anything except for a 3. That one can't be a 3 because then it would be 4 threes. So 10 digits take away the 3, 9 choices. Now, another way you could do it is you could have your 3, your not 3, and then your 3. Okay, so you can see that there are 4 different ways of that happening. And really all I did to figure out my 4 ways was I shuffled the not 3 digit. So I did the not 3 digit in the last, the third, the second, and the first position. That's how I found out that there were 4. So just filling this in here, all of these choices, 9, 1, 1, 1, you can see that 1 times 1 times 1 times 9, that is just equal to 9. So each one of these is 9. So 9 choices, 9 choices, 9 choices, but there are 4 of them. So 9 times 4, 36 ways that I can have a bank code with 3 threes. Okay, and then the other one, we already talked about this, 4 threes has to be all just 3s, so there's absolutely no choice there. So 36 plus 1, there would be 37 different bank codes that had at least 3 threes. Okay, let's look at this one. Now we're going to move away from pins and talk about numbers. How many 4-digit odd numbers are there with no repeats? So again, I ask you, that same question I asked about pins. Can a 4-digit, not a pin this time, number start with 0? So can I have something like this? 0, 1, 2, 3. Well, looking at that, you can see that is not a 4-digit number anymore. It is now a 3-digit number. So if a 4-digit number starts with a 0, it would be a 3-digit number. So can it start with the number 0? No is the answer to that. Okay. Other thing that I want to mention, just in case we're unsure, how do I know something is an odd number? Well, no matter how big or how small an odd number is, I can look at it and tell if it's odd if the last digit is odd. So the first, second, third digit can be anything at all, but that last digit has to be odd for it to be an odd number. Okay. And by odd, I don't mean odd like Miss Gato's. I mean odd as in not divisible by 2. Okay, so here I've listed it all out. Last digit is an odd number, so that's either a 1, 3, 5, 7, or 9. Repeats aren't allowed, so the first digit can't be 0 or the last. The second one can't be the first or the last, and the third one can't be the first, second, or last. So I know it's a bit of a pain to list all these out under the dashes, but I really feel it's the key to doing these questions successfully. So let's start with our last digit because that's where my big restriction is. It has to be an odd number. So you can see here there are 5 choices. So since there are 5 choices, I put a 5 there. Okay. Now the first digit can't be 0 or the last. So 10 single digit numbers to choose from. Take away my 2 restrictions, can't be 0 or the last. That means I have 8 choices. Okay, this second digit can't be the first or the last. So 10 digits take away 2, and that is 8. So you might be thinking to yourself, hey, wait a minute, I thought the digits were supposed to go down by 1. Why are those both 8? And the answer to that is because for this second digit, 0 goes back in the mix. So that's why they're the same. Okay, the third digit can't be the first, second, or the last. So 10 digits take away my 3 restrictions means I have 7 choices. Okay, so putting those all together in my calculator, I have 2,240 4-digit numbers that are odd with no repeats. Okay, so in this question here, this question here, we're going to look at, this is our last question, we're going to look at a couple different ways of doing it. We're going to do it with restrictions, and then we're going to do it with grouping and not grouping. So let's say that we have 5 people, Alice, Bob, Kathy, Don, Edward. Do you see what I did there? A, B, C, D, E. How original. They want to line up for a picture. Alice and Bob want to be on the ends. So I want to know how many ways can that happen. Now, being on the ends means one starts and one ends, but it doesn't specify who does what. So here's what it would look like. I have Alice and Bob on the ends. So in the first position, it could be Alice or Bob. In the last position, it's going to be Alice or Bob, but obviously not the first because we can't replicate people. So if Alice stood here, it would have to be Bob here. If Bob stood here, it would have to be Alice here. And then Kathy, Don, Edward, we have 3 people left to arrange. So looking at that, I have 2 choices for my first one, and then 1 choice here because it's Alice and Bob, take away whoever sat in the first. And then here I have 3 people left to arrange. So that's just 3, 2, 1. Okay, so I can multiply those together, and I can see that there are 12 ways that happens. Okay, let's try another one. Okay, so let's say I want to know how many ways can these 5 people sit together where Alice and Bob have to sit together. Okay, so how cute. They're probably dating, right? Alice and Bob, they're dating, so they want to sit together. So what we're going to do is we're going to group them together as though they're one object, kind of like a couple, right? So they're a couple, they're like considered one person together there. So we're going to group them together as one person. And when I do that, it's really like I have 4 people to arrange instead of 5, because I just want to make sure that Alice and Bob are sitting together. So I really have 4 people to arrange. So 4 choices for the first, 3 choices, 2 choices, 1 choice. But is that the only way that Alice and Bob can sit together? So is it have to be Alice and Bob? No, it could be Bob and Alice. So there are 2 ways to group Alice and Bob. So 4 objects to arrange, 4, 3, 2, 1, times by the 2 ways of arranging Alice and Bob. Because it could be Alice Bob or Bob Alice. Okay, so let's put that into our calculator and get our answer. There are 48 arrangements of 5 people where Alice and Bob must sit together. Okay, well sometimes, you know, couples, they have a little disagreement, okay? So let's say they have a disagreement and now Alice and Bob are saying, we can't sit together. So I want to know how many arrangements are there where Alice and Bob must sit separate. So this is where it becomes difficult. Just imagine all the cases, okay? I don't have all of them here. I just have a couple of them. Oh my gosh, they look so cute there. Okay, so they don't want to sit together. So let's say Alice sits here in the first position. Well, then Bob can't sit beside her. He could maybe sit here, or he could sit here or here. Okay, Or imagine if Alice sat in the first position, he could sit in the fourth position or the fifth position. Like, we have so many different cases, actually too many cases to solve. So we're not going to solve it that way. When it comes right down to it, there's only two cases. Either Alice and Bob sit together or they don't. Okay? So instead of focusing on how many ways they can't sit together, because we just saw in the last slide how many possibilities there are, there's just way too many. This is my advice to you in math and in life. I always want you to stay positive, okay? So let's always stay positive. And what I mean by that is we're going to do all the ways of arranging the 5 people with no restrictions minus all the ways they can sit together, and that will give us the ways that they can't, because those are our only 2 choices. They sit together or they don't. Okay, so that's exactly what I'm going to do. Now, fortunately, we've done a lot of this work already. So Alice and Bob must sit separate is going to be solved by doing all the ways they can sit together, no restrictions, minus all the ways Alice and Bob are together equals all the ways they can't. So all the ways, no restrictions. Let's do that. We have 5 people, absolutely no restrictions. So that's just going to be 5, 4, 3, 2, 1. Now let's look at all the ways they can sit together. So if you remember, we just solved that in part B. All the ways they can sit together, we already solved that, and we found that there were 48 ways. So all I have to do is take my answer for the all and subtract it for all the ways that they can. So that's exactly what I'm going to do. 5, 4, 3, 2, 1 works out to be 120. So my all minus can, all the ways, no restrictions, 120. Take away all the ways they can sit together, 48, means 72 ways that they can't sit together. So hopefully that makes sense to you. So stay positive, never solve a can't question, always solve an all minus can question. Okay, so to summarize part 1 of our lesson, repetition always allowed unless otherwise stated. Always start with your restrictions first, and that's what I'm doing by labeling underneath all my dashes. At least is a minimum, at most is a maximum. We didn't do an at most question in the notes, but there is one in your practice questions. Grouping all the objects together that must be together as one item, just pay attention to the positions or the ways of arranging those objects that you group. Objects that can't be together, the negative, always solve the positive case. All minus can equals can't. And if we have cases, as in the one that we did with the at least 3 3s, you could have 3 3s or 4 3s, those were cases. You add them together to find the total. So to end this question, to end this lesson rather, I have a question for you. I want to know how many monsters are good at math? Think about it for a minute. How many monsters are good at math? The answer? Well, none of them, unless you count Dracula.